Welcome to the second part of our two-part installment on sampling and aliasing. This lesson focuses on the concept of aliasing. The Nyquist-Shannon theorem tells us that we need to sample greater than 2 times the maximum frequency in our signal. So in the example we previously discussed with a 10 Hz sine wave, we need to sample at greater than 2 times 10 or greater than 20 Hz to accurately reconstruct the signal. The big question then is, well, what happens if I sample below this Nyquist-Shannon theorem? What if I sample below twice the maximum frequency of my signal? Well, we've foreshadowed this a bit in the previous example when we have our 10 Hz sine wave that we were sampling at 12 Hz, and we get what appears to be a 2 Hz reconstructed signal. So instead of that 10 Hz signal that I'm expecting, I saw what appears to be actually a 2 Hz signal out of my sampled signal. The basic idea is this. If I sample my signal below 2 times the maximum frequency content, so below 2 FM, we end up getting a false frequency. And that false frequency is less than Fs over 2, the sampling frequency divided by 2. And we call this the alias frequency, and we'll write that Fa for short. So when you think of the word aliasing, you're thinking of a fake name. So in terms of signal processing, an alias signal is effectively a fake signal. There's not a 2 Hz component of my 10 Hz sine wave, but the way I've sampled this signal, I'm actually ending up with what appears to be a 2 Hz reconstructed signal. So there's a bit of aliasing going on here in our signal processing. Let's explore this Nyquist-Shannon constraint then. So let's take a look. What happens if I sample my signal, in this case my 10 Hz sine wave, what if I sample the signal at exactly 2 times the maximum frequency content? Well, if I sample my signal at 20 Hz, I'll end up with various scenarios in terms of my reconstructed signal. Here's one scenario. In this scenario, I end up sampling every peak and every valley of my 10 Hz signal. And if I reconstruct my signal using a linear interpolation, I'll end up with a decent reconstruction of my original signal. So the intuition then is that if I sample at 2 times my maximum frequency, I'll capture all of these peaks and valleys. However, there is a word of caution here. If I'm sampling at exactly 2 times the maximum frequency, I may end up capturing all of the peaks and valleys. However, I'm somewhat phase dependent. So let's take a look at scenario 2. Instead of sampling the peaks and valleys, I'm slightly out of phase. So my sampling points move a little bit further down to the 0 voltage line. In this case, if I reconstruct my signal using linear interpolation again, I'll end up with a decent reconstruction. I'll still get my 10 Hz signal and my reconstructed signal here. However, if I end up out of phase, if I end up sampling out of phase, there's a third possible scenario where now I'm sampling each time across the 0 volts line here. And if I reconstruct this signal, I'll end up with a reconstructed signal of 0 Hz, of no frequency at all. Basically a DC signal here at 0. So my ability to reconstruct the 10 Hz signal here is dependent on phase if I'm sampling at exactly 2 times the maximum frequency. Now, if I sample at a frequency less than 2 times my maximum frequency, I end up missing these peaks and valleys. And this is what's leading to this poor representation of the original 10 Hz signal. So we see I've missed a peak here, I've missed a peak here, I've missed a valley here, another valley here. And this is really what's contributing to my inability to reconstruct that 10 Hz signal if I'm sampling below 2 times the maximum frequency. So in this case, by not capturing all of these peaks and valleys, I'm ending up with a 2 Hz sinusoid coming out instead of my original 10 Hz sine wave. So what's going on here? Well, this sampled signal will have a maximum possible frequency that will be dependent on the sampling frequency Fs. And this maximum possible frequency in my sampled signal is defined as the Nyquist frequency, commonly referred to as Fn, and this Nyquist frequency will be defined as Fs, the sampling frequency divided by 2, which is also equivalent to 1 over 2 times delta t, or 1 over 2 times the sampling interval. Here's a quick example of that. Let's consider that 10 Hz sinusoid that I sampled at 12 Hz. As it turns out, no matter what signal I'm sampling, if I sampled at 12 hertz, the maximum frequency that I'll find in my sampled signal will be defined as this Nyquist frequency, where Fn will be 12 hertz over 2 or 6 hertz. And you'll notice that I've written xn here, where the n is in brackets, instead of x parentheses t. And I've written that because this is a discrete signal here, composed of individual samples, right? It's not a function that's continuous with respect to time. I can predict any anticipated alias frequencies using a folding diagram. On my folding diagram, if I look at the x-axis, I'm defining fractions of Fn, fractions of my Nyquist frequency. And recall, my Nyquist frequency is 1/2 of my sampling frequency. And if I have any signal here up to that Nyquist frequency, if I sample that signal, I'll get the resulting frequency. So for example, let's say we have a 4 hertz signal that we're sampling at 12 hertz. Well, at 12 hertz, the Nyquist frequency will be 1/2 of that, so 6 hertz. And 4 hertz is less than 6 hertz, so this would show up as a 4 hertz signal in my reconstructed signal. Things get more complicated, however, when I get higher than 1 time my Nyquist frequency. If my original signal has a maximum frequency greater than my Nyquist frequency, what happens is I actually start folding back. So I'll start folding from 1.0 Fn here up to 2.0 Fn. And if I'm at 2.0, I'll actually continue to fold back to 3.0, and at 3.0 up to 4.0, and so on. And this just repeats forever. For example, let's say I'm at 1.25 times my Nyquist frequency. I'll actually alias and fall down to 0.75 of my Nyquist frequency. So my alias signal will be 0.75 times that Nyquist frequency. If I'm at 1.5 times my Nyquist frequency, I'll alias and fall down from 1.5 down to an alias frequency of 0.5 times my Nyquist frequency. And this continues. If I'm at 1.75 times my Nyquist frequency, I'll alias down to 1/4 or 0.25 times my Nyquist frequency. Now when we get to 2 times a Nyquist frequency, we'll fold down to 0 Fn. So if I have a sinusoid that I'm sampling at 2 times my Nyquist frequency, it'll look like I have 0 hertz or 0 frequency in my sampled signal. As a quick example, let's consider a 9 hertz signal that we sample at 12 hertz. So our sampling frequency is 12 hertz. If our sampling frequency is 12 hertz, our Nyquist frequency will be 12 over 2 or 6 hertz. And 9 is equal to 1.5 times 6. So we'll come up here in a folding diagram to 1.5 times the Nyquist frequency, 1.5 times 6. And as a result, we'll fold down to this alias frequency of 0.5 Fn. So in fact, if we're sampling a 9 hertz frequency at 12 hertz, our reconstructed signal will look like 3 hertz in the end. And as I mentioned, the folding diagrams continue on forever. So from 2.0 Fn, we'll go up to 2.25 Fn, to 2.5 Fn, and up to 2.75 Fn. So if I had a 15 hertz signal that I was sampling again at 12 hertz, my Nyquist frequency would remain 6 hertz. However, 15 hertz is now 2.5 times my Nyquist frequency, so I would again alias down to 0.5 times my Nyquist frequency, and I'd have the same 3 hertz signal in the end in my reconstructed signal. So these folding diagrams then, what they're showing us is if I sample less than 2 times the maximum frequency of my signal, I'll end up folding down to an alias frequency. As a specific case then, if I have input frequencies at 0.25 times my Nyquist frequency, 1.75 times my Nyquist frequency, or 2.25 times my Nyquist frequency, they'll all fall on this line here. And in each case, they'll all alias down to 0.25 times the Nyquist frequency. So all 3 of these cases will look the same in the reconstructed sampled signal. And finally, let's revisit the example we've been exploring throughout this lesson. I have a 10 hertz sine wave that I'm sampling at 12 hertz. So my sampling frequency Fs is 12 hertz, and as a result, my Nyquist frequency, which is always Fs over 2, will be 12 over 2 or 6 hertz. So now I want to determine what my input frequency is in terms of this Nyquist frequency. So my input signal frequency, 10 hertz, is equal to 10 divided by 6, this ratio of 10 divided by 6 times 6 hertz, where 6 hertz is the Nyquist frequency. So that's equal to 5/3 of the Nyquist frequency. In other words, My original signal of 10 Hz is equal to 5/3 times my Nyquist frequency, where the Nyquist frequency is 6 Hz. So if we take a look at the folding diagram then, we'll rewrite our x-axis now. We go from 0 to 1 fn, but now we're going in increments of 1/3 fn. I'll continue along my folding diagram upwards past 4/3 fn up to 5/3 fn. And once I arrive at 5/3 fn, I'll alias and fold down to the alias frequency of 1/3 fn. The output of my folding diagram then is this alias signal fa. And fa in this case will be 1/3 fn, so fn over 3. We've calculated a Nyquist frequency of 6 Hz to begin with, so we have fn over 3 is 6 over 3, or 2 Hz. Which makes sense, because when we were sampling our 10 Hz signal at 12 Hz, we ended up with a 2 Hz reconstructed signal. This is in fact our aliased frequency.